All right. We are going to do the PSAT, SAT review I told you we were going to do on Monday. I changed my mind. I decided to do it today because I wanted you to have some time to practice and get your questions answered before Wednesday if you had any questions on the stuff. I'm going to go over one additional thing with you on Monday, but I want to type something up real quick. It was something that just kind of occurred to me as we were talking about some of these questions. Because we do all of this trig and special right triangle stuff in pre-cal. We're just not there yet. So I'm going to kind of stop and give you a quick crash course in this. Just a quick, it's all it is and it's 100% review from geometry. And it does not matter what level of geometry you took and who your teacher was. This is stuff that was required to have been taught to you. If it wasn't, I don't know what to tell you. At this point, this is a review, and that's exactly what it is. But if you, this stuff was sparked by people had some questions on those I'm doing the SATpractice.org that it was talking about some Radian stuff. And at that time, I should have asked whoever those people were, I don't even remember who it was now, but there was multiple people, to take a screenshot of the question and send it to me, and I didn't think about it. If it was you and you can get back to the question, because I don't even know if you can get back to it, and you could send me a screenshot of it, that'd be great. If as you're working on the SATpractice.org some more and you come across anything that refers to trig or radians, I would appreciate it if you'd send me a screenshot so I can see some more of those questions and what's being asked of you. Because it's kind of a broad thing. Like we can say radians and you have to know how to convert, that's great, but like how are they really using it? That's something that it doesn't really say, that you have to kind of see from experience. So, and we'll talk a little bit more about that as we get through this. Or anything else random that you feel like, I know there's got to be, like I can figure this out, but I know there's got to be an easier way. And the thing that comes to mind is questions like I to the 56th power, right? You're not, and it's a non-calculator, so you can't type it in the calculator, and you're not going to actually take I to the 56th power. You'll be there forever, right? There's an easier way to do that, and we'll talk about that on Monday. I know it's something that most of you probably have seen before, but I want to type a little something, just a little, not a full lesson or anything, but just a little something up to go with it. But anything else that seems kind of random like that, if you will let me know what those things are, it probably wouldn't hurt for me to address them with everybody, so you're just a little bit more comfortable with it. The more comfortable you are with any of it, the more you can spend extra time on other stuff that's stressing you out on the test, okay? Which hopefully isn't a lot. All right, so we're going to start with a quick review of special right triangles. So there are a few different ways to teach special right triangles. I'm going to review it the way that I teach it because I teach it that way because I think that's the best way. It's a matter of opinion, of course. If you learned it where you didn't use S and L, but you used all X's, I think that is a terrible way, and I will explain to you why that's a terrible way once we get to some of these examples. And I had somebody last period say, yep, that's how my teacher taught it, and man, it got confusing when this happened and that happened. And I said, that's exactly why I don't do it that way, and I never have. So if you have a 45, 45, 90 triangle, this is an isosceles right triangle, so we know that these two sides are congruent. And since the legs are congruent, we're going to label them with L for leg. L, L, and then what would the hypotenuse be? L squared root of 2. Very good. So if you can label a 45, 45, 90 triangle like that, then you can solve it. It's a piece of cake. If you take all three sides and you divide it by L, then what you're left with is 1, 1, and the square root of 2. Okay? And then you could draw a little 45, 45, 90 triangle, label the sides 1, 1, and square root of 2. Then you could do a similar triangle type proportion thing. That works too. Okay? That's another way to teach it. But I think that when you're first learning it, it's a little bit easier to learn it this way and get through this, but definitely not with X's. Then we've got 30, 60, 90 over here. So we don't use L's because the legs are not congruent. This is 30, so across from that is S for the short leg. That is not a 5. Make sure you can read my handwriting. Make sure you can read your own handwriting. My S's look like S's. The problem is my 5s sometimes look like S's, so it can get confusing. And I've seen plenty of students confuse themselves too, but that's an S. And then the hypotenuse is 2S, and then the long leg is S times the square root of 3. So if I divide all three sides by an S, then that leaves me with 1 for the short leg, square root of 3 for the long leg, and 2 for the hypotenuse. Okay? All right, so to go and actually use this, do you always have to label everything? No. If I was teaching you this from scratch, I would make you label it, even if you think you didn't need to at the beginning. But we should all be past that. And when you finished all this up in geometry, you should have been at the point where you don't really have to label all of them anyway. If you want to, that's fine, but you should be comfortable enough to just see the pattern. But I know it's rusty, we've got to knock some of the cobwebs off, so it's fine. I mean, I'm never going to suggest that you jump into just knowing and not labeling stuff. But if you're there, that's okay too. This is a 45, 45, 90 triangle. So what you should know is that this is L squared of 2, right? And that means that what is x? 10. What is y? 10 squared of 2. See, L squared of 2. Like you don't even have to do any work. You don't even have to label it. If you feel like you need to label it, then that's absolutely fine. There's nothing wrong with that. But if I label it that way, then it's got to be 10 squared of 2. It's the only thing that makes sense. So then we move on to number 2. It's another 45, 45, 90 triangle. Is this going to be 16 times the square root of 2? No. So if we label L squared of 2, it's very clear that x and y are going to be the same length, right? Then we can use this to get us a little equation. L squared of 2 equals 16. What do we do to get L by itself? Divide by the square root of 2. When you divide both sides by the square root of 2, you end up with 16 over the square root of 2. Then what do we have to do? Rationalize. So I take the square root of 2 over the square root of 2. That gives me 16 square root of 2 over 2. So what is that? 8 square root of 2. That's what L is. And since both of these are L, this is 8 square root of 2 and 8 square root of 2. So sometimes there's a little bit of work, but not always. Okay, what questions do you have at this point? All right, number 3. This is a 30, 60, 90 triangle, so there's no L's. Across from 30 is the short leg. Across from the hypotenuse is 2 times the short, across from the hypotenuse. Across from the right angle is the hypotenuse, and it's 2 times the short leg. And then the long leg is s times the square root of 3. I label mine in the exact same order every single time so that I don't get them in the wrong spot. Okay? The more consistent you are, the better. So we've labeled it, but I don't know that we need to actually show a whole lot of work necessarily. If 2s equals 8, what is s? 4. So that means x is 4. And what is y? 4 square root of 3. Okay? And maybe you could have done it even without labeling, just seeing it. But again, sometimes just writing down the labels so you don't get things mixed up is not a bad idea. So then on number 4, this is 60, so this is 30, so this is the short leg. Hypotenuse is 2 times the short leg. This is the short leg times the square root of 3. Now here is one very good example of why I think using x, 2x, and x squared root of 3 is a bad idea. Because if I'd have labeled this x, 2x, and x squared root of 3, right here I'd have 2x and x, and basically they're equal. Does that make any sense at all? No, and it makes it very confusing. Rarely are your variables s or l, so those work out just fine. So what I need is s to be able to figure everything else out. So I'm going to use this part right here. So I know that s squared root of 3 is equal to 27. So what do? Divide by the square root of 3. Then I have to what? Rationalize. So I get square root of 3 over the square root of 3. So that's 27 square root of 3 over 3. And that's what? 9 square root of 3. And is that x or is that y? Y, because it's s, right? So this is 9 square root of 3. So then what is x? 18 square root of 3. Very good. Okay. What questions do you have? Don't worry. If you liked this stuff and you liked Trig, we're about to hit that stuff hardcore, and so much stuff will start to make sense. When we get to that unit circle and everything starts to come together about why we did what we did, it'll be really good. But this is just a crash review right now. All right. So let's talk about trig. A trigonometric function is a function whose rule is defined by a trigonometric ratio. So you'll hear me use those terms interchangeably, like what is the trig ratio or what is the trig function that we use. They're kind of used interchangeably there. A trigonometric ratio compares the lengths of two sides of the same triangle. Whereas usually when we do proportions, we're looking at the hypotenuse of this triangle related to the hypotenuse of this one, but we're finding ratios from just one single triangle here. And the Greek letter theta, which you should already be familiar with, looks like this. And that is your generic missing angle, just like x is usually your generic missing side or something. So instead of using x, we're using theta. In order to solve anything with trig, you always want to figure out which angle it is that's your important angle in your right triangle. That would be this one. And then you label your triangle accordingly. Across from the angle is the opposite side. Across from the right angle is the hypotenuse. And then adjacent to the angle that's not the hypotenuse is the adjacent side. And I label, again, in the exact same order every single time I ever label a triangle. I do the opposite side, and then I do the hypotenuse, because those are the easiest. Then the last one's the adjacent. It's the one that's most often labeled incorrectly, and it's because you're not being consistent and you're not labeling all three, okay? So what is our acronym that goes along with trig? SOHCAHTOA, very good. SOHCAHTOA. I challenge you to find anybody that knows anything about trig and has never used SOHCAHTOA, okay? I mean, there's some other things out there, but they would at least know SOHCAHTOA. Like, it's been around forever, okay? So, but you have to spell it correctly and know what it means or it doesn't do you any good. This tells you how to set up your ratios. The sine of theta is equal to the opposite over hypotenuse. Opposite over hypotenuse. The cosine of theta is adjacent over hypotenuse. Yes, and it's not sin, cos, and tan either. Okay, and then tangent of theta is opposite over adjacent, and that is how you set these up. And if you can label triangles and set that stuff up, the rest is a piece of cake. Yes, sir? Oh, that's fine, because we rarely actually label that anyway. Yeah, and the only reason I don't do it, well, I don't know why I don't do it over here, probably is because some people's O's and A's look the same, and I don't want you to think it's a 0, but no, that's fine. I'm fine with that. All right, and so then find all three trig ratios. Now, there are actually six trig ratios, but you only talk about 3 of them in geometry. We'll get to the other 3 in here. I'm pretty confident the other 3 aren't an SAT thing because it just doesn't lend itself to that. But we're going to find the 3 trig ratios for theta. Make sure when you're working on trig problems that you are reading the directions and you understand what is being asked of you so you're not trying to do too much and then you're confusing yourself, okay? So the first thing I'm going to do is label my triangle. This is my theta, so this is opposite. This is hypotenuse. This is adjacent. All right. And then in order for me to find sine, which is opposite over hypotenuse, I need the hypotenuse. Like, they're not asking me for a side length, but I have to find it whether I like it or not. So how can I'll say it's x because I don't know what it is. How can I find that? Pythagorean theorem, exactly. That's how you find the missing side of a right triangle, right? Pythagorean theorem. So 16 squared plus 30 squared equals x squared. So what's 16 squared? 256. Good. What's 30 squared? 900. So x squared equals 1156. So let's just say that we want to assume that this is a perfect square, okay, because maybe we're not sure right now. You could do a big old factor tree, but you could also kind of reason through some things. If this is a perfect square, is this number bigger or smaller than 30? Bigger, because 30 squared is 900, right? Is it bigger or smaller than 40? Smaller, because 40 squared would be 1600, right? So it's in the 30s. We know that much. So now I want you to think about the last digit of whatever the number would be is going to have to square to give me 6. So what are your single digit numbers that square to give you something ending in a 6? 4 and 6, right? That means your only options here is that this is 34 squared or it's 36 squared. Make sense? And so you're going to have to check them. And which one you check first, maybe you could reason through that. Is 1156 closer to 900 or 1600? 900. So I would probably try 34 first. You with me on that? It's just kind of a little bit of a reasoning thing, so you don't have to check them both. So check them and let me know which one it is. Or you can just sit there and stare at the wall or stare at me, but I don't know how that makes you a better math student. So. This would all be non-calculator questions, by the way, 100%. It's 34. If you square this one, you get 1156, so it's 34. All of you that were wasting time waiting for somebody else to do it for you, congratulations, and yeah, good luck with yourself, by the way. Anyway, so you got 1396 for 36 squared? Okay. Well, I don't know. He said I got 1396, so I was wondering. All right. So now that I have this, and this is 34. Sine of theta. Sine is opposite over hypotenuse. So I'm going to put 16 over 34. Can I reduce that? Yes. That is 8 over 17. So the sine ratio for this angle is 8 over 17. That is the answer. You do not need a calculator for any part of this. That is what it is asking you for. So going forward and doing other stuff makes absolutely no sense at all. So then cosine of theta is adjacent over hypotenuse. That'd be 30 over 34. And that reduces to what? 15 over 17. Good. And then tangent theta, opposite over adjacent, that's going to be 16 over 30. And that gives you what? 8 over 15. Okay. All right, everybody okay with all that? That's just asking you for the ratios. Now, the next one says, given the ratio for cosine, because it gives me that one, find the remaining ratios. So I'm going to draw a triangle and label it. Here's theta. That makes this the opposite, this hypotenuse, this adjacent. So it gives me that cosine is 2 over 3. So the cosine of theta is adjacent over hypotenuse, so it's going to be 2 over 3. Does this mean that the triangle that we're dealing with for sure has side lengths of 2 and 3? No, it does not. Just like if you look over here and this is 8 over 17, this does not mean that the opposite side is 8 and the hypotenuse is 17, because these were the side lengths, right? It's some multiple of them, but that's not necessarily the side length itself. But it doesn't matter because they didn't ask me for the side length over here anyway. But I need, in order to find the other ratios, I have to find this one. And I do that how? Pythagorean theorem. So x squared plus 2 squared equals 3 squared. So x squared plus 4 equals 9. X squared equals 5. And x equals plus or minus the square root of 5. But do both of them make sense? No, it's only the positive one because it's a side length. Just like over here, technically, that was plus or minus 34, but then minus doesn't make any sense. So now that I have that, sine is opposite over hypotenuse. That's the square root of 5 over 3. Tangent is opposite over adjacent. That's the square root of 5 over 2. Okay? And if I'd ended up with the square root in the denominator, I'd need to rationalize, but that didn't happen, so, and I can't reduce those, so it just is what it is. Okay? What questions do you have at this point? All right, flip it over. All right, so now we're going to actually find side lengths. So this is SOH, CAH, TOA. Right. So it says find the value of x, round to the nearest thousandth. All right, so here's my angle. I label my triangle. This is the opposite side. This is the hypotenuse. This is the adjacent, but I'm not even going to label it because I don't need it. They didn't give me anything there, and I'm not looking for it, right? So now, which trig ratio uses opposite and hypotenuse? Sine. That would be sine. Okay? So I take the sine of what? 64. So the sine of 64 equals the opposite over hypotenuse, so that's x over 25, right? Then I want to get x by itself, so what do? Well, I multiply both sides by 25. So x is equal to 25 times the sine of 64. Now here's where you would type it in the calculator, but you're still not touching them yet, because we're not even going to touch them until we're completely finished with this side of the notes, and then we're going to go back. I have my reasons for that. So we're just going to have to basically pause on that one, okay? But that's where you would finally touch the calculator. Now we move on to number 8. Here's my angle. This is opposite. This is the hypotenuse, but I'm not going to label it. And this is the adjacent. So what uses opposite and adjacent? Tangent. Opposite and adjacent would be tangent. So okay. Tangent of 47 is equal to x over 12. So what do? Multiply. X equals 12 times the tangent of 47. And then we just wait patiently to get a calculator to finish that up. Okay. All right, so now let's look at number 9. Here's my angle. This is the opposite side. I'm not going to label it. This is the hypotenuse. This is the adjacent. So what uses adjacent and hypotenuse? Cosine. So the cosine of 18 equals adjacent over hypotenuse. So am I going to multiply both sides by 34? No. Am I going to divide both sides by 34? No. I need to get x out of the denominator. So what do I multiply by? X. I multiply both sides by x so that those cancel out. And I get x times the cosine of 18 equals 34. And then, yes, I divide by cosine of 18. Those cancel out. So I get x equals 34 over the cosine of 18, and then I wait patiently until we get a calculator. Okay? What questions do you have? All right, then you do number 10. TOA is not a thing. It's sine, cosine, and tangent. The rest of them make you sound uneducated. It does not make you sound funny. Just going to throw that out there. Well, let me say this like I always say this. If you walk in and your doctor's name is Dr. Smith, do you say, hello, Dur Smith? No, because you sound like a moron. Sin, cos, and tan are abbreviations for sine, cosine, and tangent, just like this is an abbreviation for doctor. Okay? Opposite, hypotenuse, adjacent. So the tangent of 35 is equal to the opposite over the adjacent. So then I multiply both sides by x. So x times the tangent of 35 equals 9. X equals 9 divided by the tangent of 35. All right. So, anybody remember what your little shortcut was to that? Because you just switch them, yeah. If you look at what you started with here and what you ended with, and then what you started with and what you ended with, in both cases, these two things just switch places. It's not magic. It's that you're doing the exact same steps every time it's in the denominator. So if your variable is in the denominator, you can just switch places. If you're not sure why, or you think you're going to switch things when that's not legal, then don't do it that way. You can do the steps. It'll be just fine. Okay? What questions do you have? All right. So now we're going to find angles. So if you know the sine, cosine, or tangent ratio, then you can use the inverse of the ratio. So listen carefully to this as well. This is sine inverse, cosine inverse, and tangent inverse. It is not sine to the -1 power or anything ridiculous like that, okay? So here's a little side note of this, because this came up earlier too. If I have the square root of x equals 14, and I want to get x by itself, can I divide by the square root sign? No. Twee, can I divide by the square root sign? All right, sit up, please. Can I divide by the square root sign? Because it makes absolutely no sense, because the square root sign doesn't exist by itself. Make sense to you? So when I want to get theta by itself, I do not get to divide by sine. That makes absolutely no sense, because sine does not exist it doesn't have any value by itself. You do the opposite. The opposite of the square root, or the inverse of the square root, is squaring it. The inverse of taking the sine is sine inverse. So if the sine of theta equals x, then theta equals the sine inverse of x. If cosine theta equals x, then theta equals the cosine inverse of x. And here, theta would equal to the tangent inverse of x. Okay? That's how you get it away from it. In order to work these, you start off the exact same way you did on all of the rest of them. You identify your angle, and you label the triangle. This is the opposite. I don't care about the hypotenuse. This is adjacent. Which trig function uses opposite and adjacent? Tangent. So that means I'm taking the tangent of the angle, the tangent of theta, is equal to the opposite, which is 8, over the adjacent, which is 14. Can I simplify that fraction? Yes. Do I care? No. There's absolutely no reason to reduce that, because you're wasting your time and your brain cells, and you're possibly going to reduce something wrong. You definitely don't want to introduce anything that you could make a mistake with. You're about to type it in the calculator anyway, so you let the calculator do it. What I want is theta. So in order to get theta, I'm going to have to take the tangent inverse of the other side. And then once I put that in the calculator, it'll all take care of itself. Okay? Bless you. Everybody okay with that? So here, this is theta. This is the opposite. I'm not even labeling it. This is the hypotenuse. This is the adjacent. Okay. Say that one more time. I didn't hear what you said. Yes, that is absolutely fine. And that's the way actually, and some people need to, you know where you are and, so you don't mess things up. There's absolutely nothing wrong with labeling all three of them. But then the way I actually teach it is when you label all three, then you look at it and you say, okay, which one don't I want? And then you can mark that one off. But yes, it's always safer just to label all three, but you're only ever looking at two at a time. But it's fine that they're all labeled. So yes, I'm fine with that. So what uses adjacent and hypotenuse? Cosine. So the cosine of theta is equal to 38 over 40, which again I could reduce, but I don't care. And theta equals the cosine inverse of 38 over 40. And we wait on the calculator on both of those as well, okay? What questions do you have? We're good so far? Review, right? All right, so now let's talk about radians, because this is what really sparked this review, was that radian stuff was coming up. And I mean, it's good to review all the rest of the stuff, kind of goes along with it too. But when we get to radians in here, we're going to go very far in depth with all of this, and you will for sure understand exactly what a radian is and how it works. Because this is a review, I'm going to explain it quickly. If you do not completely comprehend what a radian is when you leave today, that's not the end of the world. Comprehending what it is and how it works, not so important for the SAT. Important for later, and we'll get there. The important thing for the SAT or PSAT would be being able to convert and use it. And you can definitely use it without fully understanding what it is, okay? But I would never just leave you there. It's just not necessary right now. So here's a triangle with a sector shaded in, right? This is the radius, and so is this. So we know that these two pieces are congruent. Well, this right here is also the length of the radius. So it's almost like an equilateral triangle, except it's not really a triangle. So you have the radius in there twice as line segments, and then you have the length of the radius wrapped around the circle. So if I continued that around the circle, that radius would go around the circle 6.28 blah, 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 blah times. 6.28 is 2 pi. So basically the radius fits around the circle 2 pi times, whatever the radius happens to be. If the radius is 1, then the circumference of the circle is 2 pi. A radian is just a different way to measure something. Just like I could measure the length of this floor in feet, or I could measure it in inches. It's just a different unit. So degrees, how many degrees are in a circle? 360. So there's 360 degrees in a circle, and there are 2 pi radians. So 360 degrees equals 2 pi radians. Which means 180 degrees equals what? Well, it equals pi radians. Yeah. Right. This right here is what you need to have a concept of to get you through any of the radian problems that I've seen that might come up. Because that's basically what it says in like what could possibly be on there. It's about converting and using them. Although the way that I have seen them be used is in a way you would never be asked in a classroom of any sort. Because remember, this is a reasoning test. It's not a content test. You have to have some content, like a concept of this, to get through and reason through a question that you haven't seen before, or a type of question. But if you know how to convert, it makes it easy. All you have to worry about is just like converting feet to inches. There is 12 inches in every 1 foot. There's 180 degrees in every pi radians. If you can convert those things, you're golden. So I'm going to show you the little equations and then just tell you how you know which way to go with it. If I have degrees and I want radians, so my end goal is radians. I have some sort of degrees. My units is degrees. You're either multiplying by pi over 180 or 180 over pi. This is going to be pi over 180 because you want to divide the degree units out and get the radian units into it. If you do it backwards, your numbers don't make any sense, so it's kind of hard to do it backwards and think that what you have is reasonable. And then degrees, you would take whatever radians you have. Oh, except it would help if I spelled it right. You would take whatever radians you have, and you would multiply that by 180 over pi. Because you would be dividing the radian units out and getting the degree units in. Whatever you want to end up with is what's in the numerator. If you want to end up with radians, radians are in the numerator. If you want to end up in degrees, degrees are in the numerator. It's the easiest way to think about it. All right, so here I'm going to convert from degrees to radians. So I'm going to multiply this by pi over 180. If all you're having to do is convert, I promise you it's a non-calculator question. You can very easily knock out these zeros. Then, how many times does 3 go into 18? 6. So 3 goes into 3 once, goes into 18 6 times. So your answer is pi over 6. When we actually get to this and we actually talk about the unit circle and things start to all kind of make sense, all kind of come together, you're going to have to know that 30 degrees is pi 6 radians. You have to just know them. You don't have to know them now. You have to know how to convert now. But we're getting there. And I'm going to help you through it. This is how you learn it, and we get there. But if you don't know those things and you refuse to ever learn it, you will never get through calculus ever. Okay? I'm just telling you that right now. So you can't just avoid it like you've been trying to avoid fractions your whole life. All right, so now I'm going to multiply this by pi over 180. 150, you'd have to just know what that is in radians also. But right now, all you have to do is convert. So I'm going to knock out the zeros. What can I reduce those both by? 3. So this is going to leave you with 5. This is going to leave you with 6. So that gives me 5 pi 6 radians. Negative 220. Something that should have come up in geometry is, yes, you can have negative angles, and yes, they can be a whole lot bigger than 180. But for right now, whether or not you understand that, you just need to know that it can be that. And so we're going to multiply this by pi over 180. Put that over 1. And I can knock out the zeros, and then I can divide these both by what? 2. So I'm going to make sure I put a negative 11 up here so I don't lose my negative sign. And then this is 9. So you get negative 11 pi over 9. Okay. Now we're going to go the opposite way. We're going to convert from radians to degrees. So since I want degrees, my degrees are in the top, 180 over pi. Then the pi's cancel out. I don't want to multiply 4 times 180. I can reduce this. 3 goes into 3 once. How many times does it go into 180? 60, right? So you get 4 times 60, which is 240. Okay. So then we're going to multiply this one by 180 over pi. The pi's are going to cancel out. Now, with these two, you can always start little. I mean, you can do it in multiple steps. It doesn't have to be in one. These are both even, so I can divide them both by 2. That'll give me 90 and 18. What can I divide both of those by? 9. So 9 goes into 18 twice, goes into 90 10 times. Can I reduce again? Yes. 1 and 5. So in the end, what is my answer? Negative 25 degrees. Because you have this 5 and this negative 5 right here that have to be multiplied together. Okay. All right, so go ahead and do number 18 on your own. We'll get there. I'm not doing that right now. Absolutely not necessary right now. Okay, what's 7 times 45? 315. All right, any questions at all? All right, so I want you to grab a calculator out of the pink bucket. And there should be a box of batteries in the bottom, I think. I think I put them in all there because they don't have batteries in them. So you have to put the batteries in them. If you don't have enough batteries in your bucket, or if I forgot to put them in there, let me know. Is that empty? Okay. Are there no batteries at all? Okay. All right, that's just empty one. Okay. All right, when you turn this on, I want you to clear the RAM. That is 2nd plus 712. And I need you to listen. This is, you're either going to get an 83 like this or an 84 on the test on Wednesday. When you get them, they are all cleared. The default on the calculators is radians. If there is a question, now if you're doing this right here, you're not actually pushing any trig buttons, so it really doesn't matter what if you happen to get a calculator for that, it doesn't even matter. But up here, if you were going to push sine, cosine, or tangent, and you're working in degrees, it better be in degree mode, right? So how do I get it in degree mode? Mode. Go to mode, and arrow down to degree, arrow over, and hit enter, and put it in degree mode. Then I want you to go back and type all these answers in that we didn't type in. So 25 times the sine of 64. And you get x equals 22.470 because it says round to the nearest thousandth. Okay, so go ahead and do all the rest of them that you needed to do for a calculator. And then when you get to the inverse ones, remember that to get to inverse, you got to do second. So second, tangent, or whatever. And if you've got units, the units need to be on there. They'd be degrees for those. So double check that you get what I get. Once you've got them all typed in, and you know how to work on the calculator with it, then I need you to clear, but go ahead and finish first. But once you finish, I need you to clear the memory, which is second plus 7, and then you have to arrow to the right twice. Right, 1, 2. It'll say resetting all. And then it'll say mem cleared. Once it says mem cleared, show somebody at your table that it actually says mem cleared and not RAM cleared. Then you can turn it off and put it back in the bucket. Okay? No RAM cleared. It needs to be second plus 7, right, 1, 2. But make sure you get them all typed in first. No, don't take the batteries out. Leave the batteries in. Leave the batteries in. Thank you, though. But I want them cleared so we can use them for the PSAT. They're already, their memories. And you can throw the little boxes back in there, too. Right, 1, 2. Are you in degrees? Well, don't switch it. Why'd you switch it back? Did I hear my name? I'm sorry. We're good? Oh, I need to give you the assignment.